Okay. So, yeah. Hey. My name is Peter. I am from University of Maryland, a PhD student. Cornelia from Muller is, and Jan Sullivan is our sort of my co-advisor, kind of. But Janis is the principal investigator. I work on hyperdimensional computing, and I'm not at all in metacognition, but after talking to Paulo over the last few months, turns out that these things have more in common than I thought. So this presentation is sort of going to revisit some prior work that I've done, reinterpret it through the lens of metacognition, and show that actually there's a lot of useful things to gain out of this right off the bat. So let's jump right in. I'm going to start with a thought experiment. Marty, we're going to build a brain, Marty, all right? And of course, Marty McFly will probably say, geez, Doc, I don't know how, man. It's fine. We're going to strap something to our head. We're going to see every neuron that activates in real time, all right? So the presuppositions here are that you've been having your brain scanned your whole life. Since you were born, you had that thing strapped to your head and you've been going, right? Supposition number 2. Suppose that we also kept a record of every time you performed an action in response to what you're experiencing. We'll call that an event, all right? Question, or several questions actually. Can you build a new brain that behaves like you? Like a completely different brain from yours? Essentially cloning yourself. Can that brain simulate you after that cloning to a high degree? And lastly, can that brain explain why you behave the way you do? Right, so those are sort of the 3 things we're going to be thinking about here. Well, I mean, the problem seems simple enough, right? It's a correlation problem. All we need to do is model the changes between brain states over the events, such as these. Maybe this is the activation pattern you're seeing, right, over the events. Now, neurons are complicated, very complicated, especially a bunch of neurons. So, too complicated. Fine. Let's just make an activation of the neuron a 1 and a non-activation to 0. Let's simplify the problem, just to make this doable for us. So we're going to slap on top of this an abstraction where I'm just sort of labeling each neuron with a 1 and a 0 and showing the connections between neurons. Of course, not to scale, right? So some more simplifications on that end. But now it's all sort of tangled and hard to look at, right? So let's give each neuron a proper position so we can order them in a nice ordered way. And then things become a little more nice looking, right? So, okay, we're looking good there. Now again, this is not to scale. There's actually way more connections to these things than I'm showing you. I'm just showing some of the local ones, really. Too many connections. So many that, like, I really doubt they're doing anything. So I'm gonna simplify it even more. From a global perspective, I'm gonna assume these connections don't even matter. I'm just gonna do that. So get rid of the connections too. And voila. Michael Fassbender or Magneto, however you want to know him. Show me the real brain state. Perfection, just the vector of 1s and 0s. Awesome. So, now we're ready to begin. We need to model how we transition from this to this in time. Clearly, these are binary, right? These are digital signals. And so I need some way of doing a digital transfer function from one to the other. How do we express the difference between these two to be able to do that? Any takers? Any guesses? Right.
XOR.
XOR. But that's cheating. You already know the answer. XOR, yes. Yes, XOR, the bitwise XOR. If you do the bitwise XOR, you're going to have the mapping that turns EI into EI plus 1, simply by applying that XOR result. So, fine. It looks like we're almost there, right? We just now have to figure out how these mappings come together, right? So, some finishing touches to do that. We have our transition operation. We have a list of transitions that we generated from this. What do we do with this list? What now? We need to somehow summarize that list as one state of the brain. So we have to summarize a bunch of states as a one-state system. How do we do that in takers? Not you. You already know. Well, let's take some inspiration from quantum. Let's superpose them. We're going to stack them on top of each other. How? Well, again, take inspiration sort of from quantum. We'll do what's called a Hadamard. So an XOR and a superposition of the XORs. The way you do this is you simply add up the vectors, and for each position, if the number of ones is bigger than the number of zeros, which is just a complement in terms of the count that's possible, then that's the bit that comes out as output. So in this case, you get a 1 at that position, and so on and so forth. Now, you'll see there comes an issue when there's a tie, of course, with even things. So an easy way to resolve that, I should say, is just a tiebreaker. So flip a coin, whichever one you like, 0 or 1, it doesn't matter actually. We're simplifying this even more, right? Okay, there we go. This is our mimic brain. Free from any connections, free from any structure other than its order of nature. Looks cool, but how do we use it? Okay, it's nice we have it, but like how are we gonna make it start mimicking stuff, right? This is not yet clear. Well, we should know that XOR is an involution operation. So it is invertible by nature, and it is its own inverse. Meaning that if I just XOR with the right thing, I can get back either the A or the B, whichever one I want. So we can recall brain states, both the inputs and the outputs, whichever one we desire, with XOR. But that's for a single example. What do we do with the superposition? Well, let's look at it as a statistical problem. The number of ones versus the number of zeros, we can model that as a bunch of Bernoulli coin flips, which of course becomes a binomial distribution. As the number of coin flips approaches infinity, this becomes a normal distribution. And if we interpret the coin flips as Hamming distance, which is just the difference between the XOR between two vectors and the number of ones in it, an ideal match of 0 would correlate to essentially an impossible correlation. Like the red region over there is where it would be, somewhere way over, even probably many standard deviations over. So vanishingly unlikely it will never happen. Right? And we're going to leverage that to figure out what our output state is. All right? So some algebraic formulation of our mimic brain, right? So the model is a superposition of these states XORed between each other, right? If I take E sub I, whichever one of the E sub I, whatever I want, and I XOR the model with that, XOR is roughly distributive, so you can sort of distribute it over the terms of the summation. What you'll find is that you can sort of aggregate all the destructive correlations, where like if E1 and, if EI is not obviously E1 or E2, then you essentially have two random strings that are very long, and you're going to wind up in this midpoint here, somewhere. So no statistical correlation. But specifically for the E sub I to E sub I plus 1 transition, there, these will approximately cancel. Approximately. And so what it really look like then is the state EI plus 1 is what you get out of it, plus some random ones. So, there we go. That's how you figure out. Yes, there's noise in there. That looks bad. So it's an approximation of EI plus 1. But what you find in real life when you try to do this out, and there is indeed a correlation of how you experience the world forward in time, you'll find that actually it's going to be usually over there in the red region, significantly enough, while almost all the brain states possible will be in the middle. And so you can use that as your inputs over and over again to simulate what you do. So here's our simulation algorithm. Take the very first brain state you ever experienced, XOR with your model. The result is the new brain state, XOR that with the new model. Yes, you'll get noise every time, but that noise will never increase or decrease throughout this process. Might have to generate the model, but you'll be behaving similarly to the original person. Now, the interesting thing is as the number of neurons in our brain, so the length of the hypervector approaches infinity, any list of state transitions that are assimilating can be perfectly simulated. So with a much bigger brain, you can actually approximate not just the neuron transitions, but the neurons themselves as a finite state of time. And there we go. There we go. You built a brain. All fine and dandy, but how do we get the model to explain itself? We need to give it the language of communication. We need to attach something that us humans can understand to this process, right? Not just this like nebulous momentum in time that we can interpret, but the model itself. So that's why we changed our problem statement. We have to add some sort of symbolism into this pipeline. And we'll do that by just making a set of distinct dictionary entries that we find meaningful. And we're going to assume that we're actually transitioning from a state of your brain to one of these dictionary entries. All right? Now, the problem becomes pretty well defined in terms of communicating with another AI, such as ourselves. It can tell us what it's doing and why. So if you experience a first event, you can search through all the possible dictionary entries that you have, and the one with the lowest Hamming value, or Hamming distance, will be the one in that red region of the Brittle distribution. And it'll probably very, very likely be the only one. So that's the output class. That's what the brain is telling us that it's doing. All right. You can visualize this as such. This is a neat diagram, I guess. I'm just going to call these some symbols something normal, like cat, dog, horse, why not? You can almost view it like classification, right? But it's the same process. When you XOR with a new image that looks similar to the superposition of other images of that type, you essentially will destructively interfere with the other classes, but for this specific class, this will collapse to almost an illusion, allowing you to find the dog vector as the minimal Hamming distance match. So, you answer my question from the beginning. Sounds good, right? Perfect. Amazing. But, I mean, come on. Really? This isn't going to work. Come on, right? It's a nice thought experiment, but this is clearly not going to work, though. Oh, but I've actually done. Here's one of my papers. This is submitted to Science Robotics. With very, very, very limited resources, essentially a Raspberry Pi, we're able to solve the problem of ego motion to the level of the CNN using just 2 kilobytes of data per our model. That's essentially the vector. And we sort of cheated because we used a very special camera called a DVS camera. Now, wouldn't you know what the DVS camera sees? Events. That's what they call them in time. Literal events in time. So these are the events that our brain will be seeing. And the nice thing about the event cameras is they only see motion, essentially. And so they will not activate wherever there is a motion. So the only thing that's passed in to the pipeline is wherever you see texture. It's a sparse image. So, here's an example of how it might look. So this is it navigating an angular space. This is a self-driving car, so how it's turning, right? You can see the full probability output space as it's going. You can see that nicely defined line of passage through it, right? Likewise, this is linear speed, x-axis speed. So yeah, looks good. But why stop at a camera? Why stop at a camera? Why not do it to neural networks? Take a neural network and learn to behave like it, or at least at the output level. You can do the same thing, and this is another paper called HD glue. Actually, in this paper, we ended up gluing the neural networks together to form a consensus model that performs better. You can also error correct these models, so you can spawn a different hypervector model and take the linear combination of how often they get things wrong, how often they get things right, and make a sort of optimal vector that error corrects itself. This is very metacognitive. I don't know how else to call it as an adjective, so I'll call it that. Here's an example of a symbolic level version. So this is another paper where we did sort of symbolic learning from hashes of images. And the hash network is, of course, a neural network, and we sort of expanded its hashes into hyperdimensional lengths and let them combine with each other there. So an image will pass through the hash network, give you this hashed hyperdimensional vector, you project it upwards, and then you have the same sort of inference structure I showed before. As the network is learning, this is its performance. Here's the hypervector that's simulating. It already knows what the neural network is going to learn. If you're wondering, it does reach exactly that 65% performance, bootstrapping the entire learning process. You can see it in all these networks. These are mostly just visuals to show you what I'm talking about. So if you have any questions, I can answer them a little bit. But then you could fuse these together and you also get a boost in performance, essentially for free because there's very little overhead to train these things. I'll stop there and I'll move on to the last few slides. Some other additional capabilities that I've sort of thought about. One thing you could do is essentially bind your hypervector model to only activate within a certain radius of itself. Essentially a radius where you're always correct. And that way you actually get a model always get the answer correct for what you give it. Or it'll tell you, I can't solve it explicitly. All right? Very useful, very metacognitive. Memories. You can structure the summations over time to form memories. The distinct segments of time superposed into one. This is something that hasn't really been studied too much. Definitely metacognitive. Finite state automata. Any graph can be turned into hypervector, any tree can be turned into hypervector. Definitely metacognitive. Category theory. Category theory has a very special topic called Topos theory. That actually perfectly models how hypervectors work as disparate transforms between spaces. Right? The Topos theory essentially bounds all modern day machine learning animals. You can't really go beyond it. You can go to the pre-Topos with LLMs, that's not enough. You can't go beyond it. If you could, well, you might just be a human level AI. The analogy is sort of like, you could go up the mountain directly by a gradient descent in this like cartoonish straight line. Or you can just take a helicopter. But you have to figure out that there's a helicopter, right? So that's what the hypervectors are doing. And that's why they're so efficient in the Topos space. That's it. Here are the references for the papers that I mentioned here. There's a sneaky one at the end that snuck in with the Topos theory. You can see there's no 4 there. That's actually my most recent paper last year at IJCMF, where we were able to, do some stuff in the category theoretical space with hypervectors. So check that out too if you want. Any questions?
One or two questions, Peter?
Good.
All right, so it feels like I have to ask this question. This is very impressive. Have you tried it with brain data?
No.
With real brain data?
No.
Damn it.
And until recently, I wasn't aware why I was getting excited by all these biomed people. But now I know they use it in medical imaging because it's like perfect for sparse medical images and stuff. And I've seen them in finite state automata beside me and stuff like that, and I was always wondering what's going on. But yeah, I should do something about it, but after I graduate, yeah. I gotta focus on that first. Yeah. Any other questions?
All right, well, let's thank the speaker.